very much. Thank you very much for the introduction and the invitation. It's I'm glad to be here and to talk a little bit about what I've been doing. And today I'm going to talk about this paper that is just now on archive, which is called Flow Stability for Dynamic Community Detection. And it's a work that I've been doing with Jean-Charles Delven in Louvain and with Renaud Lambiot here. And so, as you can guess, it's about a method for detecting communities in temporal network. So temporal networks, in case if you don't know what they are simply a way to capture time-resolved interactions. And what is really nice about them is that they allow to represent complex temporal patterns that are not captured by static network, such as, for example, burstiness or memory or non-stationarity. And to give you a very simple and short example, if you take this network with 3 nodes, A, B, C, that has 2 edges, and the first edge is active at a given time T1, and then becomes not active, and you have a second edge that becomes active at T2. Well, in this network, if you consider that it's a temporal network, it means you can actually go from A to B to C if you respect time, but you cannot go from C to B to A because there's no temporal path that go in this direction. This means that if you take a temporal data and you represent it as a static network, you will have those kind of paths that actually don't really exist, but that are present in static representation. So that's why sometimes it's better to actually use a temporal network. And there are, of course, actually different ways to represent temporal networks. If you consider that time is discrete, you can use, for example, just a sequence of static graphs, right? Like you see here. Or if you consider that time is continuous, but you can also have just instantaneous edges, where, as you can see here, you have a network where there are some times associated to each edge, and the edge are just active at some given times. Or you can consider a continuous time and also edges that have given duration. So you see that here edges are active only during a certain durations. And actually, this is the representation that we used. And this is also the most general one, because you can represent the other ones as special cases of this interval graph representation. So, of course, one thing that people like to do when they have networks, and static networks, but also temporal networks, is community detection. This is, of course, very useful because it allows to extract a kind of coarse-grained representation of the network and to simplify the understanding of what is happening. And when you have a temporal network, you also want to have an idea of the dynamic of the communities. And there are different ways to do that, but most methods actually aggregate some of the activity over some time windows, or rely on the assumption of an underlying stationary process. And we were interested to develop a method that didn't use those assumptions. And actually, we thought first about actually what is the meaning of a temporal community in this context of temporal network. So if we go back to the static case, we have assortative communities, which are usually defined as some densely connected group of nodes that are more densely connected to each other than to the rest of the network. And this implies a symmetric relation between the nodes that you use to cluster nodes together. So now if you consider a temporal network, actually, this notion of density is not well defined if you just look at instantaneous time, because if you just look at just a really short snapshot, well, the network typically will be very sparse, and you actually don't have a good picture or who is connected to whom. So we think that to have a notion of density of connection, you must consider some time range of the network. But then we don't want to aggregate the network because you will lose temporal information. But also what we saw is that if you remember, when you consider a time range, actually the relations between the nodes are in general asymmetric. So what can we do? Well, our idea was the following. We don't want to use any temporal aggregation. We want to keep as much temporal information as possible. And to compare nodes in a kind of symmetric way, we compare the synchronous evolution of a diffusive flow that starts on the different nodes. But now, since we are in a temporal network, this diffusive flow, we don't know if it will eventually reach a stationary state or not. So we also need to have a method that does not rely on this assumption of stationarity. So how can we do that? Well, we want to use this idea of a diffusive flow, which is here actually simply random walks. And this is something that has been, as probably some of you know, well used already in the study of static networks. And the idea is that if you look at the dynamics of a diffusive process on the network, you will actually learn a lot about the structure of the network. To give you a simple example, if you consider this network with different clusters that are shown with different value of this alpha parameter, and you consider a stochastic process x of t that is defined by the sequence of values alpha I observed by a random walker on this network. And now you want to find a way to measure the quality of the partition that you define here. And actually, what you can say is simply that your partition is good if the random walkers are more likely to remain within their starting cluster. Right? They will stay in the same cluster for a long time before eventually leaving the cluster to jump to another one, if the partition is actually well aligned with the structure of the network. So how can we measure this? Well, simply by using the autocovariance of this process x of t. So it's simply the expectation of x of t times x of t plus some time tau. So you want that after some time tau, this stochastic process has the same value. So it means the random walker is still in the same cluster, minus what you expect for two independent random walker. And actually, if you develop this framework, what you find is what is called the Markov stability of a graph partition, which is this function here that depends on the time after which you look at, I mean, the time over which you let the random walker evolve, and this matrix H, which is the partition, which indicates the partition that you have chosen. Basically, what you see here, this expression actually is exactly this the same thing that this autocovariance. It's the probability of starting on some node and being on another node after a time t, minus the same thing for two independent random walkers at stationarity. And also what is nice with this framework is that if you look in particular at t equal 1, you find that this is equivalent to optimizing the classic Newman-Girvan modularity. So the question is, how can we try to do something similar but for a temporal network? So we have to define a covariance that is does not rely on the assumption of stationarity, because as I said before, in temporal network, you don't know if your random walk will reach a stationary state. So actually, it just means that now the autocovariance or the covariance depends on T1 and on T2, so the starting and the ending time. And if you define those different values, like the density probability vector, just the P of t, and the transition probability matrix between T1 and T2, then you can actually find that this temporal covariance is given by this matrix. Where here, actually, if you look at element ig, it's exactly that. It's exactly this covariance. It's the joint probability of being on I at T1 and on node J at T2, minus the same probability for two independent random walkers. But here you see that we actually have a problem, is that we are comparing one node I and one node J at two different times, one at T1 and one at T2. So it's not really a synchronous comparison. So this is not really what we want, to put nodes together in the same cluster. We want to compare them at the same time, but also take into account the evolution of the network. So how can we do that? Well, actually, we can do that by considering those two covariances that we call the forward and the backward covariance. And actually, they are built simply by considering the inverse process transition, right? So if you consider the diffusion that starts at time t with a vector p of t, I start at time t1, sorry, with a vector p of t1, and you let it diffuse until some time t, then actually this inverse process transition is the matrix that will make you go from t back to t1. So actually it's inverse diffusion, and it actually makes you go back to t1. And you can actually compute it using Bayes' theorem, because those transition matrices actually contain conditional probabilities. And if you simply multiply the covariance matrix that we had before by this inverse transition probability, what you find is the following. And you can see that as a diffusion process where you let random walkers diffuse until some time t, and then they actually, then you look at the inverse process and you go back to your initial time t1. But another way to see that, if you look at element ig, now it contains the joint probability that two walkers start on I and j at t1 and are on the same node at t, minus the same probability for two independent random walkers. So it's actually exactly what we want. And this, you can see it as a way to cluster together the sources of this random walker flow. And since we cluster the source, we also want a way to cluster, if you want, the sinks of this flow. And this, we can do it by looking at this backward covariance, which actually we define exactly like the forward, but now looking by reversing time. So if you have some time interval, t1 until t2, you can look at the forward covariance starting in t1 until some time t. And if you want to cluster the sinks, so you can simply look at a process that starts at the end on t2 and diffuses, but backward in time. So it will diffuse backward in time. You just look at the reverse evolution of the network, and you do the same thing to actually cluster nodes in sinks of this process. So now
can I ask a question? Sorry. So
sure.
What do you mean by clustering sources and sinks? So you will cluster of all nodes, no? So
you cluster all nodes in source and in a sink cluster, if you want, in a forward and a backward cluster. But they are in the two nodes are in the same source cluster if the random walker that starts on them tend to stay together during the evolution of the network.
And the other way around for the sinks.
Yeah, the other way around, but looking with the reversed time evolution. Right?
Okay, thank you.
So now we have something that is looks at a synchronous comparison. So we compare nodes at the same time. It also means that the matrices that we use now are actually symmetric. If you look, actually, they contain the product of T and the transpose of T. So that's why they are symmetric. And also, we don't need to make any assumption on the stationarity of this process. So we can define two quality functions. So for a time range T1 until T2, we now, so it's, if you want, similar to the Markov stability function, but now we look at this forward and backward covariance, and we want to integrate them from T1 until T2 or T2 until T1, and then cluster this with a forward partition and a backward partition. So those two matrices, HF and HB, are just matrices that encode those two partitions. And the idea is to find the best partition that will maximize those functions. Yeah, so it's a kind of clustering in sources and sinks of this diffusive process. And yeah, this, I think I already said that. It's also, if you want, a way to make a co-clustering of the transition matrix, because in one sense, we are actually clustering together the rows of the transition matrix, and in the other sense, we are clustering together the columns of the transition matrix. We also just need a way to compute those transition matrices, and to do that, we simply use this model of continuous time random walk. So random walkers are actually restricted by the activation patterns of the edges, and we also need to define a rate of jumping. So if you want a speed, velocity for those random walkers, which can be also measured by the characteristic waiting time. So if you look now at this simple example with 3 nodes and 6 edges, it means that, for example, during T1 until T2, random walkers can jump between nodes B and C. And actually, during all those static inter-event time, we can compute easily the transition probabilities. Actually, they are given by simply the exponential of the Laplacian. And then if we want to get the transition probability between any two nodes and any two times, we just have to multiply all those inter-event transition probabilities. And now if you want to go backward in time, you just have to do the multiplication in the reversed order. And in general, it's a non-Markovian and a non-stationary process. So now to give you a small example, we can consider this toy example where we have 3 groups of nodes, and the activation pattern of the edges is given by some probability with that is explained in this diagram, where you see that during a first time interval, we have actually nodes from group 1 and 2 that interact together. And nodes from group 3 just interact with themselves. Then during a time T2, you have all groups that only interact with themselves. And then we actually switch. Then it's group 2 and 3 that interact together. And at the end, it's group 1 and 3. So you see that here, if you want to describe this the system with temporal communities, it's not really clear what you should, how you can do it, right? And actually, if you simply aggregate all the activity and look at the static representation of this network, then you will, if you look at the modularity matrix, this is what you see. So you see that you find easily the three groups, but you lose all information about this complex interaction between the different groups. But now, if you use this temporal covariance matrix that I showed you, you see that you actually capture some of the asymmetry between the interaction of the different groups. But again, here it's not clear, and also it's not necessarily easy to do a clustering of a matrix that is not asymmetric. So instead, if you use those forward and backward covariance that I showed you before, this is what you get. And you see that here, now you actually have symmetric matrices that you can cluster easily using those two functions that I talked about. And you see that here, if you look at the forward partition, you have actually group 1 and 2 that are together, and group 3 is alone. And for the backward partition, you have group 1 and 3 that are clustered together because they were the last one to interact. So you see that now with those two partitions, you actually capture quite well the whole dynamic of this system. Something else that is quite nice is that we have this random walk rate parameter. So the speed at which the random walker actually go from one node to another node. And this actually play the roles of a resolution parameter. For example, if you consider now a temporal network that has a kind of static activity that is given by this block probability matrix, where you see that you have some kind of hierarchical structure. Well, if you look at the number of clusters that you find using this method, you see that if you change you see here it's the waiting time. If you change the waiting time of the random walker, you will find actually the different levels. But also, since, for example, if you look at walkers that are quite slow, for example, those ones that have a waiting time of 1,000 time step, you see that first, if you wait some time, if you let the simulation run some time and you do the clustering, you will find first the first level. But if you let it run longer, you will eventually find the second level. And if you let it run even longer, you will find the third level. So it means that actually now it's really a dynamic a resolution parameter, because of course it depends also on the dynamic of your temporal network. And as an example of
something,
yeah, sure.
With like letting it run longer, do you mean like shifting T2, like integrating the whole thing over longer time? Is that what you mean?
Yeah.
Like on
yeah. Sorry. Here actually it's the
okay.
time. This is the time between T1 and T2, basically.
T1 and T2. Okay. Okay.
Here, since actually here it's a case where the temporal network is more or less stationary. So actually here it doesn't change anything if you start integrating later or not. So it's T1 minus T2, T2 minus T1.
And is it something you see also if you look at this forward and backwards matrix? Do you see that like if the difference becomes larger, like the resolution changes again? Or?
So in this case, it means that the forward and the backward are the same. Because since the interaction probability doesn't change, so the activity pattern is symmetric in time.
Yeah. Okay. Yeah.
But actually, if now you take something where the activity pattern is changing with time, for example, here you have you start with a probability of interaction between nodes that is given by this, or in 4 clear blocks, and you continuously change it to become like this with just two blocks. So now, actually, if you look at the forward and backward stability, you will see that for some value of the waiting time, so when the speed actually match, so the speed of the random walker match well the speed of change of the network, you find that you have the backward and the forward a partition that correspond to those two cases. And here, just as a comparison, if you instead of using this framework, you use the framework of the multi-slice modularity, which now divides your temporal networks in different snapshots and basically apply modularity optimization to the whole multi-slice, multi-layer network. You see that if you do that, you can also find the partition in 2 and at some point in 4 groups. But if you look at the variation of information of the solution, so if you run it multiple times and you see how much the partition that you find changes, you see that actually you have some variation of this of the solution, meaning that it's difficult to actually find the good partition. While in the case of the flow stability, you always find the right partition. Because of course here it takes into account this possibility that the network is changing in time.
But just a further question on that slide. So you said if you choose the time right, no?
Mm-hmm.
What happens if you are off by a bit or off by quite a lot?
So here you see that if your waiting time, for example, is too small, you will find only for the backward and the forward, you will find only the partition in 2, because basically so if it's very small, it means they are going very fast. So they will immediately explore the larger scale, and you will lose this. But if you do a scan in the, I think here it means that you always have to do some scan of this random walk waiting time parameter to understand where actually you have some dynamic scales in your system. For example, here it's a real-world example now, which is this primary school contact network, which has been used a lot from the social pattern experiment. So it's a contact network between more than 200 children, with also some teachers. And actually it's 5 different grades, and each grade is separated in 2 classes. And they recorded all the contacts between 2 days of school. And here we applied this framework on the whole 2 days of data with initial uniform condition for the random walkers. And then we vary this random walk waiting time parameter, and we again look at the variation of information of the solution of the partition. And when you do that, you see that it seems like there's actually at least 2 minima that seems to indicate that those are the scales, the dynamic scales where you find robust solution. And if you look at those 2 scales, this is what you see. So here, what I show is for the first scale which corresponds to a random walk waiting time of 1 hour. You see here the forward partition, and here the backward partition, and how each node is actually linked from the forward to the backward partition with this alluvial diagram. And here it's the same thing, but for a random waiting time of 63 seconds. So here, what is nice is that you see those 2 scales, and at the scale of 1 hour, we find actually this division in grades, which is not perfect because, for example, here you see that for the 4th grade, the 2 classes are not together, but for the other ones, they are together. And if you look here, for example, there are also some here, for example, the 2 splits. But when you look at the data, this actually makes sense, because you can see that, for example, the average contact between those 2 classes is smaller than the average contact between the other ones. And also here you see that if you look during day 2, the first grade A and B, they spent less time together. So actually it makes sense. You also see those points, and actually that's those cluster with just 1 or 2 students, but actually it's students that were not present during the first day, but only the second day, or here that were not present during the second day, but only at the first day. So it's actually also makes sense that they are separated here. And now if you look at this scale, which looks a bit more messy, actually, what we see here is really the mixing between the different grades and classes, which is due to the breaks and the lunch that they take together. And again, you see some splits between the forward and the backward, some differences that are mainly explained also by the fact that during the first day and during the second day, they didn't necessarily spend time during the breaks or the lunch with the same classes. So if you want to have a good summary of what is happening during those 2 days, actually those 2 scales and with the backward and forward partition give actually a good picture of the dynamic of the system. Another example is this temporal contact network of 3 living wild mice. So it's really mice that are free to live in the countryside of Zurich. And actually, they have an experiment where they record the interaction of the mice just when they are in their nests, but otherwise they are free to go. So it's that data set where we have around 400 mice. And here we look at 2 months of data from actually the end of winter until the beginning of spring in 2017. And there's actually a very high temporal resolution with a million of edges. And what we did is that we looked at this time weekly intervals. So for each week, we compute the forward and backward partition, and then we look how this evolved. And again, we use uniform initial conditions, and we also vary the random walk waiting time. And again, we see that there are some minima, meaning that there are some scales, dynamic scales that seems to be actually natural scales of this system. And if we look, for example, at the coarsest scale, so for random walk waiting time of 1 second, what we see, so here I show you for each week the forward and backward partition, and then I've linked them all together to show how this evolved over time. And here it's actually pretty nice because we really capture this transition from winter to spring, which also corresponds to a case where there's no reproduction to a case where there's reproduction, which means competition between the mice. And also in winter, it's cold simply, which means that we see that in winter, since there's less competition and also it's quite cold, the mice have to form bigger groups just to keep warm. And as spring arrives, you see that a lot of the males are actually kicked out of the groups. The groups are mostly made by the females, but also they split to form smaller groups due to this competition between the mice. And also what is interesting is now we can look at this other scale, at one of the other scale at 24 hours, for example. We see that we have a quite different picture. So it's the same data and the same time range, but now we go from. Actually, what we see is that the communities are much more stable. So we see that under this picture of big communities that split in smaller groups, there was actually always this picture of very stable social communities that stay the same in winter and in spring. Simply, in winter they merge to form bigger groups, but we can still capture them by looking at different scale. And now to finish, last example. So far I used examples where we were mostly interested in the dynamic and the structure of a network. So we used a uniform initial condition for the random walk. But with this this framework, we can also use any initial condition that we want. And in particular, if we are interested more in a process that is happening on the network rather than just the evolution of the network, we can try to model this process and then cluster it. So here we were interested in capturing the influences of network scientists in the fields of physics. So we use the APS co-authorship network. So it's all the papers that have been published in the American Physical Society journals. And what we do is that we looked at we found all the authors from 2000 until 2010 that were part of the network science community, and we actually start a random walk process on those authors on this network in 2010, and we let it propagate backward in time until 1970. So we actually try to look at all the possible other authors, previous authors that were influenced for those authors of the 2000s that are network scientists. And then we can actually apply this now the backward flow stability to find the backward partition, and we do that for each decade until 1970. And so here you see the number of nodes in each decade, and you see that we start with a small number because we have only actually authors that are part of the network science community. But then, as we go backward in time, in the 90s or 80s and 70s, we have more authors because actually we let this process diffuse. But also the network itself is also becoming smaller and smaller because when we go back in time, there were simply less authors. So we have this network that is changing in time with authors that maybe were here in the 90s but not in the 80s. So we need a way to link communities together that take into account this fact that the communities can actually change, but we want to actually link them by following rather the flow of a random walker. So actually, since we have for each decade the transition matrix that we completed, we can simply look at the transition probability between clusters, right? And then we can find the ancestor communities of the authors of the 2000s by looking at the communities of the 90s that have the highest probability of being linked from a community in the 2000s. So just to now show you something that hopefully will be a bit clearer. If we here, this is an example where we start just from 3 communities in the 2000s. You see here the size of the community is the number written inside each circle. So you see we have a community here with mainly authors from the USA and from Hungary, with some famous author in the complex network community. Here in B, we have authors from the UK, Finland, and Spain, and in C, authors mainly from Italy, USA, and Spain. And then we can look at the communities in the 90s that from which, I mean, if you start from one of those communities, this is the probability that you will actually reach one of those communities in the 90s. And we simply put some a threshold to only select communities that have a probability above here 5%. And what we see is that we have here a very diverse set of communities. So the color that I show here actually indicates the number of authors that have as a main journal one of those journal from the EPS that actually also represent the main field of those authors. So we see that here, of course, most of those of the authors from the 2000s are linked to PRE, which is really the journal for statistical, nonlinear, and biological and soft matter physics. So it's really where people usually publish things about a network. But when we look at the 90s, we see also a lot of authors from physical review B, which is a condensed matter, but not only that. And we see some communities, for example, about black holes, or also phase transitions or diffusion processes. So we see also that what is interesting is that those three groups actually have quite different influences. There's a very small overlap of the communities for those three groups. But then when we go to the 80s, we have actually a bit more overlap, but still quite a diverse range of communities. And finally, in the 70s, we have now only three communities. Two are mainly from physical review B, so condensed matter about electronic structure and phase transitions. And the last one is actually mostly from physical review C, nuclear physics, with mostly about cross sections. So I guess experimental physics. So the words that you see here are actually the most frequent bigrams from the title of all the articles published in each communities. So it's just something to show a little bit the possibilities of this framework. So yeah, as a conclusion, this temporal flow stability framework defines communities in terms of forward and backward flow of a random walk process. It takes into account the time respecting path and doesn't make any assumption on the stationarity of the process. Also, what is quite nice is that in the end, it only has one parameter, which is this dynamical resolution parameter. And it really allows to look at different dynamic scales in the system. And I think it really opens the door to define new concepts for temporal networks in terms of random walk and of flows. So thank you for your attention. Yeah, you can find this work on arXiv, and of course I will be happy to answer any questions.
Thank you, Alex. Thank you very much for a very nice talk. Are there any questions? I see claps in the chat. Many people are in the chat. I can start with one. So the last analysis I found super interesting.